Hello everyone, welcome back to AEFE GOE 123. In this assignment, we are continuing to practice our skills in performing nodal analysis. Let's recall, when performing nodal analysis, we typically go through 4 steps, SAAS. The first step is to select a reference node, and that's the ground. At this node, the voltage is equal to 0. The second step is to assign the node voltage that we are going to solve. The third step is to apply KCL. We apply KCL to all the non-reference nodes. That's the n-1 essential nodes. So the last step is to solve the system of equations, the equations of KCLs. So question P2.57. So for the values of the node voltages shown in figure P2.57, then find the value of Ix. Well, in this question, the ground has been selected for us. That's here. The voltage is equal to 0. And the voltage have also been assigned for us. We have V1 here and V2 here. So what we need to do here is to apply the KCL to these two nodes. So let's get started to write the KCL equations. We assume that all the currents flow away from this node. So for node 1, we have -1 plus V1 minus 0 divided by 10 plus V1 minus V2 divided by 5 is equal to 0. And for node 2, we have V2 minus V1 divided by 5 plus the current is provided by the dependent current source. That's 0.5 Ix. So we plus 0.5 Ix. And the lost current is here. So we have V2 minus 0 divided by 20 is equal to 0. So we have two unknowns, V1 and V2, and two equations, so we can solve them. But in this case, we need to, we can see that we have an Ix. Ix is the current used by the current dependent voltage source here. Well, so that's actually give us another unknown. Well, in this case, we want to solve, our main goal is to solve for V1 and V2. So we need to find a way that can eliminate this impurity in our equations. Well, we can find that Ix is here. That's flows from the node 1 to node 2. So you use Ohm's law, we have Ix is equal to V1 minus V2 divided by 5. Well, so now with this equation, we can eliminate the Ix. With the our system equation only contain V1 and V2, and we can very easily solve them and find out that V1 is equal to 6 volt, V2 is 4 volt, Ix is equal to 0.5 amp. Question P2.58. So for the node voltages shown in figure P2.58. Well, when we are performing the nodal analysis, especially in a relatively more complicated circuit diagram, we first need to take a look of those voltage sources. Where are they located, and what type of situations we are in for this circuit? Well, so we can see that we have two current sources. So we know that this is at first the type A, the circuit with current sources. Well, we can see that we also have a voltage source. That's a dependent voltage source here. And it is connected between the reference node, that's the ground, and the other node is connected to a essential node here. Well, so we have this voltage source connected to the reference node. So that's the second type, type B1. Well, in this case, we know this is 0 volt, the ground, and this node will be 2Vx. Well, now the only two node voltages here we don't know is V1 here and V2 here. Okay, so we need to find two equations to solve these two unknowns. So let's get started from node 1. We have currents flows here, 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 and here. We have 4 currents. So that's -1 plus V1 minus 0 divided by 5 plus V1 minus, here is 2Vx divided by 15 plus here that's V1 minus V2 divided by 10 is equal to 0. Now comes to the second node. Similarly, we have current here, 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 and here. So we can do V2 minus 2Vx divided by 10 plus V2 minus 0 divided by 5. Here the current flows the opposite as we assumed, so we use -2. And here we have V2 minus V1 divided by 10 is equal to 0. Well, now we have two unknowns in two equations, and let's see, are there any impurities in our system equations? And the answer is yes, because we have a dependent source, so we have an extra Vx here. Well, so what's Vx? Are there any ways that we can represent Vx by using our target node voltage variables V1 and V2? And the answer is also yes, because we have Vx, the positive polarity, positive terminal connect to V2. So V2 is higher than V1 in this case for Vx. So we have V2 minus V1 is Vx higher. So now we can eliminate Vx by using V2 minus V1. Well, after solving this equation, this system of two equations, we can find that V1 is equal to 5.405 volts. V2 is equal to 7.297 volts. Question P2.61. Find the equivalent resistance looking into the terminal A to B for the network shown in figure P2.61. Well, for this question, we are asked to find equivalent resistance. And for this circuit, from our previous experiences, if we want to find equivalent resistance, we need to do circuit simplification. And we need to combine the resistors to get a simplified circuit. But in this case, we can see that we have 3 resistors, 36 ohm, 5 ohm, and 26 ohm resistors. But when you look carefully, we have a dependent current source. Well, we have no way to combine the current source with a single resistor directly. But don't worry, we have a hint. We can see that first we can connect a 1 amp current source across terminal A and B. So we can connect a 1 amp current source here. And then we are asked to solve the network by the node voltage technique. So our second step is to use the node voltage technique to solve the network. And the third step is to know that the voltage across the current source is equal in value to the equivalent resistance. So what this means is that we want to find R equivalent across the terminal A and B, and we introduce a test current that's of 1 amp value. So we use V test over I test, because here we have a fixed current source, that's 1 amp. So our goal is to find a V test to know what this equivalent circuit would look like. So now our goal would be to find the V test. Well, so our second step is to find the node voltages. So let's say this is V1, V2. Assume all the currents leave the node. So for node 1, we have -1, opposite direction, plus V1 minus 0, assume ground here, divided by 36 ohm, plus V1 minus V2 divided by 5 ohm. That's equal to 0. And we have another equation for node 2. So here we have V2 minus V1 divided by 5, and V2 minus 0, ground, divided by 26. Here the same direction, so AVX is equal to 0. Here we know that A is equal to 0.1, so we directly use 0.1. Well, let's see, are there any dependent sources? Yes, there is. We have Vx. So we need to know what's Vx to eliminate Vx. Vx is here, that's V1 minus V2. So we can substitute in the V1 minus V2 to eliminate Vx and solve the system equation, and we can find that V1 is equal to 12 volt. Well, so V1 is the voltage across this 36 ohm resistor here. Well, because the current source is connected in parallel, so it will share exactly the same voltage across it. So we know that we test here that the voltage across the 1 amp current source is 12 volt. So Req is equal to 12 divided by 1, that's 12 ohm. So the equivalent resistance is equal to a 12 ohm resistor. Question P2.65. So for the node voltages in the circuit of figure P2.65. Well, in this circuit diagram, we can see that there are some mesh currents labeled for us, but we can disregard this mesh currents because we are not going to use the mesh analysis here. Instead, we are going to use the node analysis, so we can ignore them for now. And so we are going to go through the 4 steps, IAAS. So the first step, select ground, it has select for us, and second, label the voltages, and also done for us. So let's direct jump to the third step, that's to write the KCL equation. But before that, it's important when performing node analysis, we need to observe carefully of any voltage sources here. Do we have any voltage source? Yes, we have. Here we have a 20 volt voltage source here. And let's see which nodes are this voltage source connected to. Well, this is the node, and this is another node. Well, are this reference node or not reference node? Well, reference node is here, so obviously these two are essential non-reference node. So in this case, we are in situation 2A, B2, B1, B2 here. Sorry about that. So in this case, we need to use the supernode. We combine everything between these two nodes as a supernode and perform KCL once to this supernode. Well, let's see how many nodes we have now. We have a supernode here. Assume all the currents leave this node. We have node 2 here. Assume all the currents leave the node. We have a node 3 here. Be careful, we have 4 currents here. So we have 3 unknowns, 3 nodes, 3 unknowns. So we need 3 equations. And because we have V1 and V4 combined as supernode, so we can write another equation to express the difference between V1 and V4. So let's write the equations. So let's get started from the node V2. We have V2 minus 0 divided by 2, okay, plus V2 minus V1 divided by 4k, plus V2 minus V3 divided by 3k is equal to 0. So that's our first equation. The second equation, let's do the supernode. So we have V1 minus V2 divided by 4k here, and plus V1 minus V3 divided by 1k here, and plus here now V4 minus V3 divided by 2k, plus here now V4 minus 0 divided by 4k is equal to 0. Well, for a supernode, we have two equations. So we have another equation that's V1 connected to the positive terminal higher. V1 minus V4 is equal to 20-fold. So that's our third equation. Now, we have our last node, that's V3. V3 is here, so we have V3 minus V2 divided by 3k plus V3 minus V1 divided by 1k, and plus V3 minus V4 divided by 2k. And here the current source has a current opposite to our assumption, so that's minus 5 milli is equal to 0. Please be careful about the k and milli here. So after, if we substitute in, if we enter all of these equations in our MATLAB, or you can also try to use some linear algebra techniques to simplify the matrix, you can get V1 is equal to 20.7317 volt. V2 is equal to 9.7073 volt. V3 is equal to 60.0 volt. V4 is equal to 0.7317 volt.